So good afternoon. Welcome to this edition of the NITheCS Colloquium in a new venue. We had a little case of double bookings in the other venue. So sorry for that. And sorry to the online participants for starting a few minutes late. Yeah? So this afternoon, we have a very interesting colloquium integrating Earth systems and socio-economic modeling for South Africa. And we have two very prominent speakers, Professor Pedro Monteiro, who in the School of Climate Science, yeah, and Professor Martin de Wet, who is in the School of Public Leadership, both at Stellenbosch University. So it is a joint venture to tackle a really complex problem, which will be one of the, or which is one of the research focus area of NITheCS, where we really put a lot of effort in. And we are expecting big things from the team. Yeah. So without further ado and without any more pressure, I think, Pedro, you're the first to start. And maybe we should try to remember the questions and ask them after the second talk, so that maybe we have a better chance of sticking to the time. Pedro, over to you, please.
Thank you. Yeah, I do. Yeah. Thanks very much, Francesco. It's wonderful to be here, and I've been meaning to give a talk for quite some time, actually. But finally, the right moment arose, and this is actually really cool. So 2 weeks ago, we held a national workshop at NITheCS, and we brought together members, leadership of the different of the science in what you might call the different Earth system domains, the ocean, the land, and the atmosphere, as well as the human system in the form of our second speaker, my colleague, Martin de Wet. So, and that in a way encapsulates one of the reasons why we're here, is that we've got excellent science in each of the domains, but we don't have a capacity to connect them, to couple them, and really get a handle on the feedbacks between them. So we're calling it the Earth System and Human System Modeling Platform, and I'll come to some more detail about that. This is a sort of one aspect which is important, and I hope to come back to it as well, is this is not a model for Southern Africa or for Africa. This is a model that connects Africa to the planet. So it's a global model that actually has very high resolution at the African continent and ocean scale. And that's really important because when you're talking about feedbacks, particularly the bad ones, the positive feedbacks, they are very scale sensitive. And although there are many Earth system models available globally, there actually isn't one that does what we want to do, which is have high resolution over the African land and ocean and atmosphere and have that connected to the planet. So we're running global runs, not just regional runs. Okay. Is this one? Okay. So one of the characteristics of, despite the very hot weather outside, one of the characteristics of the climate system at the moment is some feedback here. Is that we are actually in a well-behaved. Oh, it's the microphone. Yeah, no. We're actually in a well-behaved phase of the climate trajectory that we are going to be in. And in this image here, you see our emissions growing exponentially. It is a figure we all know. And we've got the uptake of the ocean, the land, and what's left over in the atmosphere, which is what drives global warming and climate change. So this mass balance here really captures it. So we've got emissions, fossil fuels, and land use change on the one side, and the actual mass in each one of the terms of the atmosphere, the ocean, the land. So one actually extraordinary feature of the system, of our planetary carbon climate system at the moment, is that when you look at, oh, there's something, can we get rid of this? Sorry, Hank. We have a term called, oh, thanks very much, the airborne fraction. The airborne fraction of CO2 in the atmosphere is the change in the CO2 in the atmosphere in a given year divided by the total emissions, okay? And one of the remarkable things about it is, despite the increasing emissions, which is the brown reddish line, the airborne fraction remains fairly constant in the last 60 years. And that has actually bought us an enormous amount of time. Because the reason for that is because the ocean and the land are actually taking up not just CO2, but heat. The ocean's taking up, of this residual CO2 in the atmosphere, 95% of the heat generated by that residual atmosphere is taken up by the oceans every year. Hence, you see the panicked papers emerging now about 23 and then 24 and 25 have been completely out of the uncertainty bounds of the mean for the past 10 years. So there's a worry that this may not continue. And if this does not continue, then a whole lot of assumptions that we make at the moment about predicting climate go out the window. And that's why we're here, is to actually put in place the capability to be able to handle that transition where positive feedbacks start to reduce the control that we have. At the moment, we have control. Doesn't look like it, but we have. And that may change. So this is from the sixth assessment report of the IPCC. The same report, chapter, remarked, so this report was finished in 2021, 5 years ago. It's incredible what's happened in the past 5 years in terms of just how rapid the transition is sort of evolving. 5 years ago, we were saying, well, actually, we see the processes that are changing, that may change, that may influence the feedbacks beginning to respond. We're starting to see, the ocean stratifying in summer more strongly, in the Southern Ocean particularly. We're seeing changes in the land. But the conclusion was that the effects are still too small to be weakening the trends that we saw in the previous figure. That's starting to change. Oops. So to understand that, I'm kind of using this cartoon. The top figure, these are two figures. Top figure is temperature, and the bottom figure is emissions of CO2. The top figure it's a cartoon, okay? So it's just a representation. The gray line represents the 1.5 degrees centigrade. That's the 1.5 degrees centigrade threshold. This, when we handed in the IPCC report in 2021, we still thought that we were going to be on that gray line. We could have got to that gray line. That's gone out the window. As we here now, we are busy breaching through that. And so the blue line is notionally the 2 degrees, and the red line is would be a 3-degree overshoot. And this is called the temperature overshoot, where we are going by a significant amount over and still bringing it down to 1.5 degrees at the end of the century. So now when we look at emissions, we see that what's associated with this overshoot is this quasi-linear increase a little bit, of course, because it's been truncated, but it would sort of start over here somewhere and be going up. And theoretically, we should have already turned down 5 years ago, peaked emissions and began to reduce emissions to stay within that gray line to be at 1.5 degrees by the middle of the century in that case. But instead, what's happening is more likely we are heading into the blue line trajectory, and there's nothing at the moment that tells us that we could be also on the, we couldn't be on the red line trajectory. So the thing about this is that there's an overshoot of carbon emissions, which is the integral of the area between those curves and this one here. In other words, we've exceeded the budget of CO2 emissions to stay under 1.5 degrees. So what needs to happen is that this has to be clawed back in the second half of the century through negative emissions. But let's first of all focus here on this, what I've called the feedbacks in disequilibrium phase. Of course, we are in a disequilibrium state, but that is going to accelerate. And this is the transition. This is why this section here and this section here is why we are thinking that what we're talking about here is necessary. So the critical thing is that we move from a period where we have extremes at the moment, like what's happening outside. But if we stopped emitting, those extremes would weaken. In other words, we would remain inside the envelope of climate as we know it. But what's happening is once you breach into the overshoot zone, you go into territory where the carbon and the climate, i.e. the carbon and the heat, start to feed back on each other. And we no longer control quite so easily the long-term evolution. So the issues like commitment, there are certain changes that will start to happen in the planet, like that we are, even if we stopped emitting, we are committed to those changes. We'll come to that in a minute. So we've got two challenges in the second half of the century. Between now and 2050, we've got this challenge of still bringing CO2 emissions down to net zero, okay? But we will have done it with this excessive CO2 emissions. And that's going to start to drive these perturbations. And then we have to be able to claw back that CO2, and carbon dioxide removal is what's the method. And one of the big concerns is that there's an assumption that we will be able to do this. We at the moment, we have no way of doing it. That's certainly not to this scale. And another fallacy, while I'm about it, I have to mention, because there's a lot of talk about carbon dioxide removal, is that carbon dioxide removal will, in the most optimistic scenario, remove 10% of our emissions. We still depend on cutting emissions to be able to get here. Okay, so and the thing here is that we have to have a platform, a modeling platform now, that is able to handle non-linearity and positive feedbacks. Okay, and we have been able to use, you often use climate models and Earth system models. And there's quite a lot of confusion between the two. Climate models were very powerful and widely used in this phase, predictable, well-behaved phase of climate. You cannot be here without having both carbon and climate processes working together, because they feed back on each other. So, for example, warmer ocean means that there's decreased solubility of CO2. which means that the ocean sink decreases. So that's just one example. And the same happens on land, with vegetation changes. There's similar examples. Right. Okay, so this is an example of this non-linearity. So we have been following this quasi-linear, actually we are here, we are roughly here. If we continue to emit at business as usual, we could go up to this point here, which is a sort of 4 degrees. Well, let's even stay at 3 degrees. And what you say is this upward trajectory is quasi-linear, but the removal is not linear at all. In fact, if you plotted CO2 and temperature separately, temperature does something like that, and CO2 does something like that. So what happens is that the temperature and CO2 that are almost fully coupled on the way up uncouple. And we need to be able to have a handle on that. Okay, so I've mentioned this point. So we've moving from a world in which models that just handle the physics of climate were sufficient, and they just prescribed CO2, the content of the atmosphere, and then had a forcing function, radiative forcing function from that, and to actually needing fully coupled Earth system models, and more having human system models that are able to link to the Earth system model. So what are some of these challenges? And these are just a few of them. Extreme events where the characteristics of those extremes change. Climate intervention, i.e. carbon dioxide removal and solar radiation management. That's going to be a huge challenge to our policymakers, business, all of us. Because so now we've got 2 different communities. One is controlling the albedo of the planet, and the other one is reducing CO2. And do we have the capacity as scientists in Southern Africa to allow our policymakers to go to the global meetings and say, actually, you can't do that, because this is probably the consequences in the region are different to the ones that the other models give. So we need to have this kind of science to back up those kind of interventions. And the problem is that they'll be happening together. And the carbon dioxide removal is one thing which is kind of probably more doable. Solar radiation management is really uncertain in terms of the albedo changes. Anyway, tipping points are really an enormous issue, and which drive this idea of irreversibility and positive feedbacks, and particularly the global Africa feedbacks, which is something we need to know. On the human side, which we'll hear more about, there are a number of challenges related to we as a region need to make development changes in the middle of this trajectory. It's going to be an enormous challenge in that. This is an example of a tipping point where the Atlantic Meridional Ocean circulation, which transports heat from the Pacific and Indian Ocean around past Cape Town into the North Atlantic, and it's what keeps Europe warm and wet and productive. So one of the concerns is that the increased melting of the ice from the Greenland is reducing the density of water in the North Atlantic, and there are observations that this AMOC is slowing down. The big discussion is, when will it stop? Well, the last time it stopped was 12,000 years ago. And this was a temperature redistribution in the planet. It cooled down the northern hemisphere and it warmed up the southern hemisphere. And the reason for that was because all this heat, which normally goes around the Cape and to the North Atlantic and keeps the Northern Hemisphere warm, stops. And it actually stays in the Southern Hemisphere. So what are the climate consequences to our region if the oceans around us continue to warm up? That we need to be able to have a handle on. And it's remarkable that given this, and we are probably in the front seats in terms of globally to be able to run a major science program to understand this problem. And yet we don't have anything like that. So that's an interesting kind of situation. Okay, so the reason why I mentioned these other additional tipping points is to really highlight the issue of irreversibility. One of the big concerns globally is that between 1.5 and 2 degrees centigrade may lie a whole lot of irreversible tipping points. In other words, it doesn't mean that we're going to see the collapse of Antarctic ice shelves in our lifetime, but we are committing future generations to that. The issues of the Amazon related to the Amazon, the changes in the Southern Hemisphere polar vortex, of which actually we're already seeing anomalies in it, and the issues around CO2 capture and removal and solar radiation management. So what is it that we're proposing to do? This is just a scheme to, when we think about our region, this is what we're talking about. It's not our region as in we normally think about it there. This is our region. This is the part of the ocean, the land that we need to understand to be able to connect in a meaningful way to the planet. And this is how we aim to do it. This is an example of a US equivalent. So what we would do is use some kind of stretch grid system. Could be a finite difference model. It could be a finite element model, which provides high resolution, in our case, over this region. And the trade-off is slightly lower resolution over the whole planet. But we are able to do runs of global runs that are giving us the coupling between the planet and the region at the scales that are required for the coupling to occur. So what we're planning to do here in this platform is to have a hub, which this is the part which would be associated with housed within the NITheCS community. Okay, so it's a hub that has integrated assessment modeling capability, Earth system models, and high performance AI, machine learning, coding expertise. And so these are a number of issues that drive the human side. And of course, what we want from the Earth system model is to be able to model the large planetary cycles, which are the ones that respond and drive the coupling between the planet and the region, and then, of course, into the human system. Okay, this is just an example to really highlight the potentially important role of AI to help us bridge the gap of existing models and their impact in terms of predicting the impacts on land and in the ocean. So this is an enormous area of research. Okay, so here's the same figure, but now with the domains linked in. So what we have are the Earth system domains here, the research institutions, universities, and research centers, all linked into these Earth system domains. These are our strengths. And our strengths lie on both sides, both extremes, but we're missing this part here. So this will be a decentralized system. This is not a science research, process research hub. it's an enabling hub. So we will have engineers and specialists who are able to do the runs which are required from the communities that sit on either extreme. Yeah. So this is really making the similar points. And I'll end. So this is a paper which was published 2 weeks ago. And I'll just give you 30 seconds to read through it because they write, these are the last 2 paragraphs in the paper. And I think that they encapsulate brilliantly why we need to do what we're thinking of wanting to do. Martin?
First part of the talk. And while we are busy reading, we can quickly swap speakers. And I think the slides are already in the computer. So Martin, thank you very much. I think the slides are on the way. Here we go.
That's not the wrong, that's the wrong one. I cannot speak to that.
Was it?
Yes, that looks good. Yeah.
Which one?
That one. NITheCS ESMIM.
That one.
9 March, yes.
Apologies for that.
Great. Okay, got it. Thank you very much. Thank you for dropping my anxiety levels, quite a few, few grades. Yes, I'm an economist. I'm from the School of Public Leadership from the Faculty of Economics Management Sciences. My work has been mostly around systems dynamics modeling and the coupling of ecology and economics, trying to develop smaller kind of models that's focused on ecological questions that are driven by economic activity, but also have implications on how economies function. So we cut our teeth on smaller problems like, say, the invasive alien species problem and how that relates to the economy. What we are here talking about is something at a much bigger scale. This is as Pedro has been saying, this is about a whole region and how the earth sciences and what's known about the earth and the planet is linking up to human systems in that particular region, which is a big question. So it's really a proposal of trying to link 2 worlds. Now, the reason why this is now so important is the fact of overshoot and irreversibility. We're seeing non-linear feedbacks coming through. And up to now, economic models basically assumed that things are linear and things are moving back to equilibrium. So if in a stable climate framework, you can always go back to equilibrium, even if you have to have certain extreme mitigation measures, for instance, but at least you're in a predictable environment. That is changing. So we cannot use those underlying assumptions in our models anymore. All models are wrong, some are useful, and I think as economists we have to come to the point where say the usefulness of some of our models are really in doubt now, because we're assuming a lot of things that are not real anymore. And hence are working together on this part now. So why does this really matter? In the first place, South Africa's climate risk is real and extreme. It's not just a region that's going to float through any future climate change scenarios. We've seen this in the downscaling models from the CSR. There's a lot of studies are coming out. This is real. Another thing is there's active geophysical constraints on the development paths. It's not that the economy can take care of itself by just internalizing the external costs, in our language, of environmental impacts. Those environmental impacts are now determining the pathways of development. So what you'll see is that water scarcity, land degradation, heat stress are active determinants of economic pathways. It's not that the economic pathways can be corrected for some of the impacts on the environment. So it's changing the ball game. The implicit and explicit limits. Most of our work so far has been focused on the geophysical limits as resource assumptions. So the natural resources are available. We have to manage it well. There is some scarcity, which we can mitigate it through price mechanisms, for implementation of taxation, things like that. But that's not a fundamental limit to growth. And that's where the real switch comes. It's not that it's a new thing. There's a branch in economics which is called ecological economics, which has been saying this for 3 decades now. But that branch is becoming more and more important now, because there are limits to growth that are being forced upon the economic system. There's not a lot of leeway to change that now. And it all becomes a planning liability. So what's going to the national plans now is least cost optimization kind of modeling, which assumes equilibrium, that equilibrium can be reached. And it ignores binding biophysical limits on the national development paths, which is sometimes brought in ad hoc in a political way, but not through the modeling platforms. Not that it's entirely ignored, because you cannot ignore it, but it's not organically part of the modeling platforms. So that leads to unsustainable development pathways. So where we are, I think Pedro has shown this figure in just in a different way. We have an integrated assessment of the economy, energy systems, the land use, the human side of things, climate impacts, the Earth systems models. These are the cycles that are going through planet, and that climate affects water, land, and extremes that shape development pathways. That becomes the important thing. Where do you start the modeling? You start on those places where the development pathways are really influenced. Then human decisions on energy, land, on policy, those things are feeding back into the emissions. Of course, that's nothing new. What is new is that we need an integrated policy that's based not on least optimization modeling, but on connected models between the Earth system and the economic or the human system. So there are certain gaps in the current South African modeling framework, the integrated assessment framework, or those kind of models that try to link the economy with some kind of biophysical aspects. The one, it's very one-way asynchronous kind of modeling. It's going one way. So you get your pre-computed ESM outputs, like National Climate Information System. That's the scenarios that feeds the models. And then the models at the end will just go back into the policy domain. There's no feedback. There's no way of understanding how the biophysical domain is constraining the economic development path. You're just assuming it's not. And that's okay if you're in a kind of a stable climate envelope. It's not okay if you're going to overshoot any irreversibility. The second one, there's a theoretical economic bias in many of those models, which lean towards equilibrium. And they lean towards the effect that standard optimization is at the end of the day what you want to achieve. So you want to have as least cost economic outcome for the environmental problems that you have identified. That is a general equilibrium framework. It's computable general equilibrium framework. That's a CGE kind of modeling that we macroeconomists have worked with for a long time and still working with. But they cannot capture the complex nonlinear interactions between the economy and the environment. They're not part of that. They're assumed out of the modeling architecture. The third one, it's an important one for a country like South Africa, where we're not homogeneous. in terms of our society. It's a very unequal society. Distributional impacts are very important across different groups of people. There's social heterogeneity and bounded rationality drives world transitions and creates equity concerns. So you really need to make an effort to understand that there's no single representative agent who's acting in terms of rationality, but there are many different agents that behave in many different ways. And that's not, I mean, it's been taken care of with agent-based modeling, even in standard economic modeling now, but it needs to be connected to the Earth Systems modeling community in the region we live in specifically. Then the fourth one is that biophysical constraints in the terms of the amount of energy that you need to invest in a transition towards a more safer planetary outcome is often neglected. So yes, we're investing in energy efficiency, for instance, as a climate policy, but the investment in energy efficiency is not achieving what you want to achieve through the rebound effect. So the rebound effect at the end of the day just leads to an economy that uses more and more energy because we're just using the gains that we've got through energy efficiency somewhere else. It's not going back into less energy. It's just going back into more growth. It's going back somewhere else. So there's a kind of almost a second law dynamics of the thermodynamics. The second law of thermodynamics is completely ignored in economic modeling. It's not seen as a concern. If you start talking about irreversibility, it's definitely becoming a concern. And then the last point is that few South African integrated assessment models in the economic space is open source. It's all proprietary information. You cannot access the code. There's here and there's a bit of databases that's been shared, but you cannot get into the model. And it's owned by Treasury, it's owned by some universities, it's owned by certain places. You cannot build as a community, you cannot build and work on that model unless you're part of that group. So it's a bit of a problem for reproducibility and community development. So this is the platform. I'm not going to say too much about that. So integrate that in the platform. It's an open, modular, community-based modeling infrastructure. So I think that's where NITheCS Associates, and I think that's where the vision is, where people can contribute to this in very different ways. So where do we want to go? This is using Dieter van Vuren's work in 2012 about the kind of integrated assessment and ESM coupled models. He was thinking about that about 15 years ago already. You start from the one-way asynchronous, where we are in South Africa now, and you move all the way to the fully coupled. And each one has got benefits and costs, of course. The benefits in terms of very flexible, transparent, using existing tools. You can do it on the fly quickly. You can get some good results out, but you miss the feedbacks, the inconsistencies in, let's say, the thermodynamics. There's certain checks that are not part of the modeling. You have to do that all externally. And then you move towards a fully coupled online model where it's synchronous, two-way, and that's best for nonlinear tipping points. You need to have that. But it's higher cost, it's complex, it's less flexible, but it doesn't mean that you need not to invest in it. At some point, if you want to say something about our futures, you need to go there because we are moving into that kind of space. In between, I mean, that could be the pathway towards. It's either improving the economic models by getting some Earth systems reality in them, and that's already happening with water, energy, food kind of nexus models, and then improved ESMs where certain social rules are constraining some of the use of land, water, things like that. Okay. So who's in this network? In NITheCS, I mean, you know who is in the networks, but just to quickly remind ourselves, I think it's more analytical, mathematical, physics, computer science, but also economic, social science, humanities, and bring that together into a shared interest in the theory, the computation, and climate society futures. Now, how could that work? This is a suggestion. These are possible roles. From methods to computation, processes, society, and policy are all part of where this platform wants to have an impact. So how to couple system dynamics, agent-based modeling, the emulators is where mathematicals, climate science, physics students, and supervisors can play an important role. That's you need to make that connection. How to run large ensembles efficiently, high performance computing, AI, machine learning, data science expertise. That's really important on the computational side. On the process side, the representation of the water, energy, food ecosystems, how to bring that together. Environmental sciences, Earth system scientists, ecologists. Then on the societal level, where economists and social scientists and humanities can provide a function, is to add how to add heterogeneous behavior, justice elements into policy proposals. And then for policy and the policy process itself is how to co-design scenarios with stakeholders. So all these questions are important. One leads to the other, and that can include everybody in the NITheCS community. So just a few things to start a discussion, to have some idea about where things can go. I think in the first instance, quick wins, mapping and matchmaking. Where are we in the different spaces? If you start working with social scientists and economists, we speak different languages than Earth system scientists and modelers, mathematicians. So how could it be a living registry of researchers, models, and data? The second one is open infrastructure pilots. Small open pilots in Python or R and coding, linking one ESM output for one socio-economic module. Can we demonstrate success in linking things on a small level? And then student-led mini projects where you start really diving into some of these pertinent questions around coupling. The methods, the emulators, net energy analysis, the thermodynamics. There are different projects that can be identified on an honors and master's level and supervision. On the longer run, that moves into semi-coupled regional IAM and ESM prototypes. You need to show prototype before you can do the full coupled model. Biophysical realism, as I've said, thermodynamics, energy return on energy invested, net energy analysis in the models, and then the fully coupled online synchronous two-way model will obviously be the flagship that you want to come out of this kind of process. This doesn't happen in a vacuum. The IPCC AR7 and the CMIP7 scenarios are already moving in that direction. And the question is how we can contribute to the science on the tipping points in extreme events and the nonlinearities. And that's going to be very important information in the IPCC assessments coming up. All right, so just some options I've put on one graph here. There's international partners that are already working on this ESM-IAM coupling, also with extreme events and tipping points, listing some of them here. The European Union's got a specific project on that, how to bridge this complexity on the ESM 2025 one. The Locomotion, the Pantheon, and some other investments are integrated assessment models that really take seriously the biophysical constraints to the economy, so they upfront that in the modeling. And there are some players there, and there are many others that have global assessment models. Some of them are helpful for the South African situation, others less so. All of them miss what's happening in our dynamics, but you need to have a coupling with them at some point. So some collaboration opportunities maybe to start with is it's a kind of a reading group to see what kind of languages we speak, just to exchange ideas. A methods clinic, it's short sessions on systems dynamics modeling, ABM, agent-based modeling, emulators, open tools. Coding sprints, can we do the coupling? Can we bring things together? Joint supervision, of course, visiting exchanges, and then proposal teams that's working for kind of a NITheCS, NRF, DSI proposal calls. See how we can build a system that fit these things together. So where are you? You're probably in one of those, or maybe most of those circles. You have a lot of skills. You have a lot of interest, or working with data and models in different domains. You have a lot of energy and ideas, and that needs to be brought together and see whether that really fits the development of a platform like this. So if you have methods and interest, if you have ideas about student projects and supervision, if you have international links that can activate things like this, I think at some point we need to have a platform where we can share this and see how to take this forward. So next steps, maybe just for the next few months, need to discuss this is mailing list and collaboration, setting up things, reading group methods clinic, and then before the end of the year, at least some pilot projects where IAM and ESM models are really coupled on a small scale to show some quick wins. Thank you.
Thank you very much, Martin. So now we know how to proceed. Thank you. Are there questions for both Martin and Pedro? Surab? Sorry.
Thank you very much for your talk. Just wanted to find out what will be the infrastructure of this project. So is it a network of people, or is it something that requires some space in the computer server? Can you maybe tell us a bit more about that? Thanks.
Yeah, that's a great question. So the idea is definitely not to duplicate the CHPC, for example. We would contribute to, so we would be using existing infrastructure to the extent that we can. But for example, we've already identified that the limitation is not computer processing capacity, because the new 4 petaflop machine we can use half of that capacity to run one of the big models. And it's storage, which is going to be a real issue. So for example, investing in storage capacity is definitely going to be something to think about. But otherwise, the models, we are not building models from scratch. The idea is to partner with one of the international models that suits our science questions the best, and have a 10-year partnership with them, where we don't only use their model, but we parameterize the processes for the Southern Hemisphere, and generally, and Southern Africa particularly. But they also work with us in terms of training of postgraduate students, and by sending postdocs here, sending our PhDs there. So we want to build something which will put in place the science. We cannot anticipate what are going to be the challenges even 20 years down the line. We may be completely wrong. But we do need to have the people and the capacity to be able to address those problems. And so that's really one of the big challenges here. I don't know, so it's partly hardware, but the actual software part of it is really important part of the development. And so the links with complexity modeling colleagues here and AI, etc., are going to be really critical.
Yeah. Here, Christian. Sorry.
Thank you for interesting presentations. My question comes from the perspective of somebody who's a physicist, therefore thinks about the world in an extremely simply minded way. If I or my students do computer simulations on physical phenomena, there's a relatively good protocol and solid basis that we understand of when the simulations are producing something that they shouldn't be producing, based on our understanding of physics principles, and these mappings are well explored. How do I understand, if one looks at these kinds of hybrid systems that you're investigating and you're putting in definitely non-physics things, how does one go about in checking or verifying or convincing oneself that it makes sense from some other perspective? This is not a criticism, it's just a question from a physicist.
Yeah, I mean, that is such an important issue, and it really points to the need for this evolving dialogue between the observationalists and the modelers. And that one of the problems is very often that the observations that are required to assess whether this makes sense or not, are not done at, for example, the correct scale, and so it's really a huge challenge, and for example, you see that emerging, in model biases, which are, and some biases appear in all the models, some biases appear on some of the models, and the most IPCC. So I try to not motivate this on the basis of the IPCC, but around the science that we need. And IPCC contribution will be a spin-off, but the IPCC tries to, because the IPCC is trying to provide results which kind of go to your question, and the question is, how confident are you about this, and how likely is it? That's really those are the two questions. And the modelers try to deal with that by saying, well, actually, all the models have their own characteristics of variability and biases, etc. So an ensemble approach, it's kind of central limit theorem kind of approach. You put them all together and you end up with something which is kind of closer to what you need. So at the moment, it's as imperfect as that. And which is why actually here, I would say there are many groups around the world who are doing this, and we don't need to join them, but we do need to actually get through some developing our science so that we can actually eventually have a model that in fact is good. Does that answer your question? Okay.
Actually, I'm going to weigh in and give an additional piece of an answer. I mean, one of the ways is by looking into the past and analog conditions to see whether something that happened in the past we can simulate, like the Younger Dryas, the reversal because of the slowdown or shutdown of the Atlantic overturning circulation. But there's another thing I want to say, and that is that the current models of climate impact costs were largely developed by an economist called William Nordhaus, who won a Nobel Prize for this work. And it is based upon the most simplistic and highly likely incorrect assumptions on how city GDP relates to mean annual temperature across the US. So what Nordhaus did was he looked at these figures across the temperature range and came to the conclusion that warmer cities had a lower GDP. And from that projected something like that. I may be imprecise on the exact details here, but projected the optimum temperature for economic growth from this relationship. And it's wrong in so many ways, because cities adapt to the temperatures in which they exist. So those GDPs have been adapted over time to those higher temperatures. That's only one reason why it's wrong. If you want to learn more about this, chase an economist called Steve Keen, who analyzes this on he's got lots of YouTube videos. But he's a serious economist. Anyway, so it's much worse than you think. Our assumptions of how the economy is going to respond may well have been massively underestimated. And in fact, it's starting to look as though they were.
Any reply to the comment?
Yeah, it's a statement which I agree with. Not much more to say than that. But other than that, I think that a lot of the economic models that has been developed since are a little bit more realistic in certain assumptions. So William Nordhaus was one of the early guys, so that's very, very, very simple model in a sense. But that's the problem with most economic models now, is that there's no realism in terms of what's happening in the biophysical world. It's an assumption of natural resource scarcity, which can be corrected through the price mechanism. In the first place, and then maybe through some other institutional and policy levers, which has its value in a stable climate environment. I think you can assume a lot of things about, you can assume, make a lot of wrong assumptions about the biophysical world if it's pretty stable. But if things are changing non-linear with irreversible, and a lot of feedback mechanisms, that becomes really problematic, and it starts affecting the economic pathway outcomes as well. So I think economic models are more realistic in behavioral, how people behave to things, especially more agent-based models are much more realistic than just rational expectations. So that's where a lot of gains has been made, but not on the biophysical side.
Okay, here, question.
Thank you. I really like both your talks, first of all. Thanks. I was wondering, so you have this plan that seems very ambitious, and it's going to take at least 10 years, right? So aren't you worried that you end up with a good model, maybe too late? Like you arrive at the moment where we are kind of already at the problem. So like the model will be like, well, you know, we know that this now is very warm kind of thing. Like, are you worried that you may be like, you know, you arrive too late essentially, and then we cannot do anything about it essentially?
Do you want to start?
Yeah, I think the process is just as important as the outcome. So the moment you raise the debate about it, I mean, just standing as an economist will invite my next talk to Department Economics, and that's important because we need to have that discussion about the assumptions of the models that drive your policy frameworks. And I think that discussion is just as important than the fact that we have this nice Rolls-Royce model one day. I think it's, and then all the students that you get into the process, and you start developing masters and honors and PhDs with them on certain aspects of modeling itself. As Pedro said, we don't know where this world's going to end, but at least we can prepare people to say something about it. I think that's more important than even the outcome.
But the process itself is really gives you a lot of like positive aspects essentially.
Yes. Yes.
Any more questions?
Just a quick point. So the point I was sort of making earlier, that we can't anticipate what the needs, the challenges, and what are going to be the questions, the problems, etc., in 10 to 20 years' time. Never mind end of the century. But what we can do is put in place the capability to do that. And this is I think this is a core ethos of this, you know, is to do that, and do it in an open way, open source completely. All the code is going to be, it's a community model, so it's going to be open. So it'll be, you'll be able to pose that very important question about the physics inside that community, and test, you know, how are we thinking about this? We do not have many, we have very few answers, and yeah. So, but I take your point, you know, it could be.
Sorry, wait a second.
Are we running out of time?
Okay, yeah, no, sure. So are we running out of time? Are we going to end up with a model and by then it's too late? Well, on that question, I would remind everybody that there's a real possibility that we have a strong window of opportunity, because the human global population growth rate peaked in 2050 or 2060. And ever since then, the planet's population growth rate has plummeted. By the end of the century, it's very unlikely that we are going to have a very significantly growing population. So we've long ago reached peak population growth rate, and we will soon reach peak population, and then the population will start to decline. And with that and increased efficiencies, we may well run into a world where we have excess energy and greater efficiencies. You can't say that we're on a highway to hell when it comes to the global warming problem. There is a very real possibility that we can get on top of this in the next 30 to 50 years. And one of the ways that is going to help us do this in a, collaboratively with other countries in a very complex environment is having models like this so we don't go down the wrong road, or at least we know roughly where we're going. So I'm not at all pessimistic that a tool like this is going to arrive too late. By contrast, I think it's going to position Southern Africa extremely well to take advantage of opportunities 10 or 20 years from now, 30 years from now. And it would be dumb not to do it, quite honestly.
Thank you.
Colleagues, can you hear me in the room? Or Erasmus
Yes,
online?
we can. Yes, please, go ahead.
Oh, thank you very much. Thanks, colleagues. Great to see you, Martin, Pedro, and catching up. Interesting, the last week I was in a set of meetings with a mostly business industry community talking about systemic responses and modeling. And basically they had a little box that said the environment. And that box was basically everything that we had, that we saw in the presentations to date that unpacked the environment into the different biophysical components. And what we had as business or industry in a box in the presentations today, my industry colleagues unpacked in asset owners, investment managers, portfolio managers, pension funds, reinsurers, and so on. And what this shows me is that if we need a common language that we get out of our boxes, it's obviously not, shall we say, complete to have all the biophysical variables in environment box, and it's obviously not ideal to have all the industry variables in a single industry or business box. But I think that reflects an underlying sense of how much we know about each other. And the solution I'd like to propose is that I don't think there's a good understanding with an industry of what it means to live in a post-carbon overshoot world. I think that is completely under the radar. The cottage industry of, and I don't say that in derogatory term, I just mean there's lots of small ones, of carbon consultants, sustainability consultants out there, it does not have this understanding. And it means that understanding does not end up with an industry. And the common language there is one of risk and one of systemic surprises. And the moment we translate this idea of a system that will lower risk because we live in a new environment where the systems respond differently, I think there's an opportunity to do that. I'm curious if there's anyone in the room that have had a similar handshake to industry and have seen either this systemic language opportunity or any others to make sure that a model like this really has credibility across multiple sectors. Thank you.
Yeah, thank you for raising the point. Okay, then maybe on that note, thank you very much to the last comment, and thank you very much to Pedro and Martin. I hope this will be the beginning of a long series of engagements. And I wanted to suggest that NITheCS buys a cloud license for both Pedro and Martin so that we can have the model in 2 years. Okay, thank you very much. According to plan, there were some snacks and drinks outside. I don't know if they're still there, but that's the plan. Yeah, thank you very much. And thank you also to the online people.
Thank you. Bye-bye.